Making sense of our complex, interconnected energy systems can often feel like, well, like trying to untangle this giant, chaotic ball of yarn. It's pretty overwhelming, isn't it? But what if there was a powerful tool, a kind of master key that could help us see how all the pieces fit together? And crucially, how we can design a more sustainable energy future. Today, we're taking a deep dive into exactly such a tool.
Yes, and our core subject for this deep dive is the EnergyPLAN model. Now, this isn't just another piece of software. It's a really sophisticated computer model
Hmm.
built for deep energy systems analysis. It's been continuously refined since 1999.
Wow, since 99, that's quite a history.
It is. And the real game changer here isn't just that it performs analysis. It's the hourly detail it captures over a full year.
Hourly, for a whole year.
Exactly. This granular insight means we can move beyond just broad assumptions. We can truly understand the minute-by-minute dance between energy demand and supply, and that reveals hidden efficiencies, critical choke points, things that annual or less detailed models simply miss. It's a fundamental shift in how we approach energy strategy.
Okay, so our mission today is to really explore this energy plan model, what it is, how it processes information, and why it's become such an indispensable guide for designing the energy systems of the future. We promise you some genuinely surprising facts and maybe a few aha moments that will genuinely shift how you think about energy. Okay, let's start untangling that energy yarn. What's Energy Plan's main purpose? What problem was it specifically created to solve?
Well, its main purpose is quite specific. It's to assist countries in designing their national energy planning strategies. It provides both technical and economic analyses, helping policymakers, planners understand the real-world consequences of different national energy systems. And different investment choices, too. It's about moving beyond guesswork to, informed decisions.
So it's about the big picture national planning. But how widely applicable is it? Can a tool designed for a whole country also help, say, a smaller city or a region?
Oh, it's remarkably versatile, actually.
Right.
While its core focus is national, it's been successfully applied at the European level.
Hmm.
And yes, absolutely scaled down to local levels, towns, individual municipalities, things like that.
Interesting.
And its evolution is fascinating, too. Initially, it really zeroed in on the interaction between combined heat and power production, CHP, and those fluctuating renewables, like wind. But over time, it broadened its scope significantly. It started emphasizing the crucial synergies you get when you include the entire energy system. So now it analyzes these intricate cross-sectoral interactions between electricity, gas, district heating, cooling grids. That holistic view is really key.
That's where it gets really interesting for me, connecting all those dots. I mean, across wildly different energy types. So how does this sophisticated energy accountant actually work? What kind of financial and technical information does it need to get started? And what kind of reports does it churn out?
Yeah, think of it like a highly sophisticated energy accountant. That's a good way to put it. What it takes are all the facts about your energy system. How much energy people need, heating, power, transport, what renewable sources you have available, the capacity of your power plants, and crucially, all the associated costs.
Oh, the costs. Okay.
And what it churns out for decision makers, well, that's the complete financial and operational picture. You get energy balances, how much was produced from different sources, total fuel import, export figures, and maybe most importantly, the total costs, including any income you might get from electricity exchange. It's the full economic blueprint, essentially.
Right. And our sources mention that Energy Plan can be used for different kinds of analyses, each with a distinct focus. Can you maybe walk us through the main types? What do they reveal?
Certainly. There are three main types. First, there's what we call technical analysis. This is all about designing and analyzing large, complex energy systems, usually at a national level.
Yep.
Under different technical simulation strategies, you input descriptions of energy demands, production capacities, efficiencies, energy sources, that sort of thing.
Okay.
The outputs are things like annual energy balances, fuel consumptions, CO2 emissions, and the core goal here, the main objective, is to identify the least fuel-consuming solution. It's like asking, how can we run this system with the absolute minimum amount of fuel?
Least fuel. Got it. What's the second type?
The second type is market exchange analysis. This goes a step further. It specifically focuses on trade and exchange on international electricity markets. Now, to do this, it needs additional inputs, things like market prices and how those prices respond to changes in import and export. It also needs the marginal production costs of individual electricity units.
Marginal costs.
Uh,
So the cost to produce just one more unit of electricity.
Exactly. And this modeling is fundamentally based on the assumption that each plant optimizes its operations according to business economic profits. which includes factoring in taxes and CO2 emissions costs.
So if I understand correctly, the market analysis optimizes for profit based on those variable costs, the immediate running costs. But thinking long term, especially with more and more intermittent renewables coming online, doesn't that short-term profit focus potentially conflict with the broader goal of a stable, sustainable grid?
Mhm.
How does EnergyPlan help navigate that tension?
That's a really crucial observation, and it highlights a key distinction. You're right. The market economic simulation is based on a short-term marginal price market model, very similar to how, say, the Nord Pool market operates. It focuses on bids to the electricity market, aiming to minimize short-term electricity and district heating consumer costs, using only variable costs in its optimization. It truly optimizes the supply side only.
Supply side only.
Now, while it's mathematically possible to simulate 100% renewable scenarios with this kind of market design, it might not accurately represent how future energy markets should be designed. Because
Mhm.
today's markets, well, they're primarily optimized for dispatchable plants, right? Plants you can turn on and off easily.
Like gas plants.
Exactly. So for systems with very high penetrations of intermittent renewable energy, lots of wind, lots of solar and dollar, the technical simulation strategy is typically more accurate because it helps identify the least cost solutions over their total lifetime, especially when you combine it with cost data. It shows you the most fuel-efficient way to run things, and that often aligns better with long-term sustainability goals for these renewable heavy grids.
That is a critical distinction. Optimizing for short-term market profits versus long-term lifetime costs and fuel efficiency, especially with renewables. It's a completely different lens. Okay, that's a real aha moment there. What's the third type of analysis this tool performs?
The third type is feasibility studies. This involves calculating the total annual costs of the entire system, but under different designs and different simulation strategies. So here you need to add more inputs, things like investment costs, fixed operational and maintenance costs, O&M lifetime periods for different technologies, and an interest rate.
So the full financial picture over time.
Precisely. The model then determines the socioeconomic consequences. It divides costs into specific categories: fuel costs, variable operational costs, investment costs, fixed operational costs, also electricity exchange costs and benefits, and potential CO2 payments. It's about getting that complete financial picture of the proposed energy system.
Right, okay. This all brings us to something the sources mentioned specifically: smart energy systems. Now, if our goal is to truly design these intelligent, interconnected energy grids, how does EnergyPlan embody that concept? How does it help us achieve a smart system?
Well, if we connect this to the bigger picture, the core principle is that Energy Plan is designed to view the complete energy system as a whole, integrated. For example, the challenge of integrating fluctuating power from renewables into the grid using smart grids. That shouldn't be seen as an isolated issue.
It's not just an electricity problem.
Exactly. Instead, it's just one of various challenges
Yeah.
in approaching sustainable energy systems generally. It encourages a holistic view, seeing all the energy sectors, heat, power, transport, gas, as one big interconnected puzzle.
So what does that mean for how the tool actually works? How does it practically coordinate all these different parts to create that smart system on the ground, so to speak?
It means the tool actively coordinates electricity smart grids with using renewable energy for purposes beyond just electricity production. So converting renewable electricity into things like heat or hydrogen or synthetic gases, biofuels.
Using electricity for more than just immediate power.
Yes, and it also incorporates energy conservation and efficiency improvements like combined heat and power,
Yeah.
CHP, fuel cells. The most effective long-term systems, the model suggests, are those that combine these measures using renewables flexibly, improving efficiency with just general energy conservation. And as a direct result of this approach, EnergyPlan calculates hourly balances not just for electricity, but also for district heating, cooling, hydrogen, and natural gas, including contributions from things like biogas, gasification, electrolysis, hydrogenation, that tracking of energy flow through every part of the system that's really key to its smart approach.
Wow, that sounds incredibly comprehensive. So when you put all these inputs in, how do the calculations actually happen inside the model? What's the step-by-step process like as it tries to solve this massive energy puzzle?
Okay, so the procedure for analysis involves an initial set of calculations first.
Mm-hmm.
Then it goes into either a technical or a market economic simulation. You choose which path. And the fundamental distinction, like we discussed, lies in their objective. The technical simulation aims to minimize electricity import to export. It seeks the least fuel-consuming solution, minimize the burn, In contrast, the market economic simulation identifies the least cost solution based on the business economic costs, primarily those variable costs of each individual production unit. Maximize profit or minimize short-term outlay. So it's essentially two different ways of optimizing the system depending on what outcome you prioritize, fuel efficiency or short-term economics.
That's a very clear difference in purpose. And what about the actual energy components it accounts for? Can you give us a sense of the range of demands and production units it considers, and maybe how the model treats a few key ones differently under those technical versus market economic lenses? That might help make it concrete.
Sure. The model covers a vast range of energy demands. You've got your basic electricity needs, fixed demand, flexible demand, import-export capability. Then district heating with different CHP systems. Cooling using electricity, heat, or even natural cooling. Individual house heating boilers, micro CHP, heat pumps, electric heating, plus industrial demands, and a really comprehensive range of transport fuels.
Transport too, okay.
Yeah, everything from traditional jet fuel and diesel to biofuels, electrofuels, hydrogen, and electric transport, including battery electric vehicles, BEVs, with smart charging and even vehicle-to-grid, or V2G.
V2G, using car batteries to help the grid.
Exactly. It models that capability. Now, when it comes to specific components, their behavior really differs depending on whether you're running a technical or market economic simulation. It's quite revealing. Take wind and solar power. In both simulations, they're generally given priority because, well, their fuel's free, right? Sun and wind. But for something like hydropower with storage, like a dam reservoir, in a technical simulation, it's optimized to avoid any excess electricity production, to make sure every potential watt is used efficiently within the system. But in a market economic simulation, it would likely hold back water, waiting to produce electricity only when market prices are highest to maximize profit.
Totally different logic.
Completely. Or consider nuclear power. In a technical simulation, it's given priority, treated as baseload. It can even adjust its output slightly for what's called critical excess electricity production, or CEP regulation.
CE, that's when there's too much power in the grid, right?
Exactly. A temporary surplus, and you need to dial down production quickly to maintain balance.
Yeah.
Nuclear might trim its output a bit in that technical scenario.
Right.
But in a market economic simulation, a nuclear plant would only produce when the electricity price is higher than its own variable operational costs. Otherwise, it might ramp down or shut off, market permitting.
Wow. Even nuclear.
And then there's energy storage. Things like batteries, pumped hydro storage, compressed air energy storage, CAES, even electrolyzers, making hydrogen. In a technical simulation, these are used strategically to soak up excess electricity, mainly from renewables, or to avoid needing to fire up less efficient power plants just to meet a peak. It's all about system efficiency.
Minimizing waste, maximizing renewable.
Right. But in a market economic simulation, storage is used purely to optimize profit. Buying electricity when prices are low, storing it, and selling it back to the grid when prices are high. It's arbitrage, basically. So you see, the same technology behaves very differently depending on the simulation's goal.
That really highlights the simulation differences.
Absolutely. And the model also includes sophisticated biomass conversion technologies, biogas, gasification, biodiesel, and synthetic fuel production plants, like making hydrogen from electrolysis or even ammonia production. It shows how it accounts for these complex transformations of energy carriers, moving energy between sectors to meet demands and optimize the overall system, however you define optimize.
We've really taken a significant deep dive into EnergyPLAN today. It's crystal clear this isn't just some simple spreadsheet. It's a powerful, dynamic tool. It helps us navigate the incredible, sometimes baffling complexity of our energy future. It's almost like having a crystal ball, isn't it?
Yeah.
Showing us different paths, the most efficient, the most cost-effective towards sustainability.
Exactly. I think the model's strength truly lies in that ability to simulate diverse energy demands and technologies in hourly steps over a full year. And crucially, emphasizing those cross-sectoral interactions, seeing how heat affects power, how transport interacts with the grid. And it really throws into sharp relief those fundamental differences between the technical approach aiming for the least fuel and the market economic approach focusing on least cost or most profit. It truly emphasizes that effective energy planning requires seeing the whole interconnected system, not just isolated parts. You can't optimize just one piece in a vacuum.
So, what does this all mean for you, listening in? Given the depth and the interconnectedness that a tool like EnergyPLAN reveals, what new questions does it raise for your understanding of your local energy grid? Or even the energy choices you make every day? How might understanding these different simulation strategies, optimizing for fuel efficiency versus optimizing for market price, how might that change how we approach the big energy debates shaping our world? Something to think about. Thanks for diving deep with us.